Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Statistics 1 Distributions, Part 4, the normal to approximate the binomial. Now, this is where things are going to get a little bit confusing, but if you really took the time in the previous videos to understand the concepts of binomial and normal distributions, you'll be able to do this. What this is a situation where you have a binomial distribution. In other words, you have discrete data. So let's say, for example, you're dealing with like the number of people who own a bicycle, okay? So, and the success rate of having a bicycle is, we'll just make it easy, 50%, 1/2. So half the people have a bicycle, half the people do not have a bicycle. Just simple example. And so since having a bicycle is discrete, either have a bicycle or you don't. You don't have half a bicycle or like that. So that's a discrete concept. Well, before, when we had discrete values and we said maybe out of 10 people, what's the probability that less than 3 had a bicycle? Well, you could do 0, 1, 2. You only had 3 calculations to do. But now our data set is going to get bigger, or actually our number of samples, our trials is going to get much bigger. So let's say we have 32 people that we randomly sample, and so and because it's discrete, we say a random variable, that is have a bicycle or not, or the people who have a bicycle, is distributed binomially with 32 trials with a 50% chance of success, meaning also a 50% chance of failure. And so what is the probability that our random variable will be, out of these 32, will be less than 13? Now all of a sudden we have a much bigger sample set. So if we want to calculate this using binomial distribution, we would have to calculate all the way from 0, that is no one has a bicycle, all the way up to 12. Notice there's no equal sign. Since we're dealing with binomial, we have to consider the inequality. 13 is not included, so we would stop at 12. So from 0 to 12 is still 13 calculations. That's a lot. If we go not 13 to 32, that's still a lot of calculations, okay? So instead of doing that many calculations, when our sample set has that many in it, meaning you have all of these little lines going up, they're discrete. So the probability of 10, the probability of 11, the probability of 12, the probability of 13. If we were to put 0 all the way out to 32, okay, from 0 all the way out to 32, if we were to put the independent probabilities, it would look something like this, which is similar to a normal distribution table. So if there is enough sample set, if it fits this criteria right here, n times p is greater than 5, and n times q is greater than 5, so you have to do NP, 32 times P, 1/2 equals 16. And then you go, yes, this is greater than 5, check. And NQ, which also happens to be 1/2, I picked easy numbers so you can follow along, also equals 16, and that is greater than 5. If both of those are true, that means your sample set is large enough, and all these little lines in here are relatively compact enough that the normal distribution curve can act as an approximation for the binomial, which adds up each and every one individually, okay? So the first thing that you need to do is you look at the, again, discrete or continuous. This is about having bicycles. I just made it up for a simple example. Having bicycles, that's discrete. You either have it or you don't. So our random variable is distributed binomially. Here's the parameters. And when we look at the probability, we see that there's many calculations that we would have to do if we used the binomial system. There's like 13 this way, and what is it? About 19 the other way, okay? So either way, whether you do not 13 to 32 or whether you do less than 13, there's a lot of calculations you'd have to do. So, and if those calculations are like 5 or more, you should consider this. If you only have to do 3 or 4 calculations with binomial, that's okay. Probably about 3, 4 at the most. But if you're getting over 4, you should be considering normal to approximate binomial. Okay, so here's your criteria. You check it out. N times P greater than 5, check. N times Q greater than 5, check. That means we can use the normal distribution method and approximate the binomial. But that means we got to convert all of our information from binomial notation into normal notation that we looked at in part 3. So that's where this comes into play. So let's start with making, again, we're going to take our binomial and change it into normal. So let's rewrite our random variable is going to be distributed normally. And with normal, remember it has mu, the mean, and the variance, sigma squared. Mean and variance. So how do we get those parameters? If we want to use the normal distribution, we need to have the parameters for them. It doesn't use N and P, it uses mean and standard variance. So this is these formulas right here. It is, I believe, in your formula sheet. So the mean is just N times P. We already calculated that out is 16. Now don't get confused with variance. The criteria is just N times Q. N times P is the mean, but NQ is the criteria. For the variance, it's NPQ. So 32 times 1/2 is 16, times 1/2 again is 8. That's the variance. Okay, now remember that's variance, not standard deviation. Okay, so we have to convert our binomial information into normal distribution information. Okay, then we need to rewrite our probability. Now our probability started in binomial. And remember in binomial, because it's discrete, it means the inequalities matter. The inequalities matter. So if it says less than 13, we're not really starting at 13. 13 is not included. It says less than 13, and this is discrete. So if you're less than 13, the next number less is 12. So the first thing that you want to do is you want to rewrite your probability. I'm going to move that over here because I don't have room down here. So our new probability is going to be x less than or equal to 12. Okay, now if there's already an equal to sign here, no problem. It means you're starting at 13. But since there's no equal to, and this is discrete, we're not starting at 13, we're actually starting at 12. So you need to rewrite your probability statement, especially if there's no equal to in the inequality. You need to go to the next number down, or if it's a greater than sign, you need to go to the next number up. Okay, so that's important. Inequalities matter with discrete values because there's no in between. Now that we have that, we've first established that we can use normal to approximate binomial. Then we converted the information over into the normal distribution information system. Now we need to do one more thing, and that's what's called a continuity correction. The CC stands for continuity correction. So the plus or minus CC is the continuity correction. You're like, what is that? Actually, you already have done this. You did this back with histograms and cumulative frequency graphs where they give you group data, and the first thing you had to do is you had to look at the group data and see if the data was discrete or continuous. If it was discrete, you had to put that plus or minus 0.5 on both sides of the group. Okay, so for example, if you had a group from, say, 10 to 15, and then the next group went from 16 to 20, if you're doing histograms or cumulative frequency that require continuous data, you would first look at the groupings and you would say, oh no, there's a little gap between 15 and 16. There's no place for 15.5. And so you would do what's called a continuity correction. You would make this 9.5 over here, which is subtracting a 0.5. You'd make this 15.5, which is either adding or subtracting a 0.5, depending on which boundary you're coming from. And you would make this 20.5, which is adding 0.5 to the end. This is the same thing as your continuity correction. Okay, so you're already used to doing it, but you're used to doing it with grouped data. Now what you have is an individual number. You have the number less than or equal to 12. Okay, so here is our discrete data, and I've included the 12 in here. So here we have 10, here we have 11. So the height represents the probability. If you were to use your binomial formula, this would represent the probability that it would be 10, the probability that it would be 11, the probability of 12, so on, okay? So what we want to do is we want to make it continuous. That means our 12 needs to be spread out and fill this gap here with the 13 and the 11, okay? So I'm just going to make this one dotted. 11's coming out this way, and 13 is coming out this way, you know, like that. We want to make it continuous. So this one here is 12.5 on this side, because we're looking at this box right here around the 12. And on this side, it's 11.5, okay? So that's our continuity correction. Now, again, when we use normal, normal uses the chart that shades in all the way in the direction that your inequality is going, okay? Whereas binomial adds up each individual one. But of course, the more you have to add up, the more calculations you have to do. But if you have a lot of calculations, you can use the normal curve. So since we're doing shading, it depends on which direction your inequality is going. Since we have to include the 12, that means this whole box needs included in our shading. So since it says less than or equal to 12, less than is that way. So that means we're going to take the 12.5 and shade this way. If it said greater than or equal to, this one is the less than or equal to. If it said greater than or equal to, well, that means we're going that way. So you would start here at the 11.5 and you'd go this way, greater than or equal to. So this one is less than or equal to, you're going this, so you have to take the right side because we want the whole box that includes the 12. Or if it says greater than, then we have to start on the left side so that we include the whole box as we go greater than. Okay, so this whole box needs included for the greater than, so we start at the 11.5. Or if we're shading less than, we start on the right side of the box and we shade less than, so it takes the whole box that has the 12, it includes the 12. This number here is our continuity correction. So in other words, we're not going to use 12 when we drop our 12 down into the Z formula. Remember our standardizing formula? When we drop it down into the Z formula, we're not going to use 12 anymore. We're going to use our continuity correction because we've changed the discrete data into continuous. So just like here, we don't use the 10 and 15 anymore. We use the 9.5 and 15.5 or the 15.5 and 20.5. So our Z, when we drop this number down into the X, remember our X minus mu over sigma. So because this is less than, we want the 12.5. Okay, that's this number here. We want the 12.5 because we are going less than direction. Then minus the mu is now, here's our mu, and this is our variance. So our mu is 16, not the 32, that was the n, the number of trials. Our mean is 16 over the standard deviation. Now, when we looked at normal, the normal distribution method, this was often written as a square. Now that square isn't visible. And this is still variance, not standard deviation. But this, in our standardized formula, is standard deviation. Standard deviation is the square root of variance. So we need to do the square root of 8 to get the Z number. Once we get the Z number, then the rest of our normal system, follows the same. You look up the phi Z, take that value, look it up in the phi Z chart, and that will give you the probability. Okay, so we're following the same mental pathway that we did in part 3. But before we get to this standardizing formula, we have to do those conversions first. Converting from binomial information, or first of all, checking to see if we meet the criteria, because they'll ask that in the Cambridge question, justify your use of the approximation. So here's our justification, just like this, show that they're both greater than 5. Don't just leave it 16 and 16, show that it's greater than 5 for both. That's our justification. Then we need to convert from NP to mean and variance. We also need to adjust our discrete data based up for our starting point. Less than 13 is the same thing as less than or equal to 12. So we need to pay attention to the inequality. Then we need to do the continuity correction, which is like what you did here. So the continuity correction, this plus or minus continuity correction, that is what goes into the X value, our little X value. So what goes right here, the continuity correction in our standardizing formula. Once you have done that, and again, remember that your format is a little different. It's still variance, but since it's not written as a square, we got to write it as a square root here. And everything else follows normally after that. Okay, well, let's set up a real example from Cambridge and work our way through it. Okay, here's our first example. Let's pull it up on our screen share, see what we got. Notice it says, in a certain country, the probability that a child owns a bicycle. Well, here we're talking about bicycles again. This time, the probability that they have a bicycle is 0.65. In other words, 65% chance that they have a bicycle, meaning that you have a 35% chance that they don't have a bicycle. This letter I here says a random sample of 15 children from this country is chosen. Find the probability that more than 12 own a bicycle. Now, we're not going to do this particular problem, but if you follow the thought pattern, the first thing is to establish discrete or continuous. Well, since it's owning a bicycle, it's discrete. You have a bicycle or you don't. So this is discrete. So we would set this up as a binomial distribution, and it has a fixed number of trials, 15 sample, as opposed to geometric, which you keep selecting indefinitely until you find the child that has a bicycle. So this is definitely binomial distribution. And if you look at the sample set, it says find the probability that more than 12 own a bicycle. Well, that means 13, 14, and 15. You only have to do 3 calculations. So this part 1 is clearly binomial distribution. It's discrete with fixed number of trials, and you only have to do 3 calculations. And so that's classic binomial. When we move to the second question, or second part, II, it now says that the random sample is now 250. So notice our sample size is much bigger. Instead of 15, it's 250. Use a suitable approximation, so it gives you a hint, to find the probability that fewer than 179 own a bicycle. Well, that's 179. If you go fewer than 179, you have to go from 178 all the way to 0. That's 179 calculations. That's going to take you a while. If you say not 179 to 250, well, that's still another 71 calculations that way. So 71 calculations is still a lot of calculations to do. We don't want to use binomial method. That's why it says to use a suitable approximation. So let's go back to our board and see what we can do with this. So the first thing that we want to do is, because the information started discrete, we want to set up our notation with the original binomial parameters. So we're going to say x is distributed binomially with, now our n is 250. Our probability of success is 0.65, which means our failure is 0.35. Okay? And we set up our probability statement, our probability that x is less than, fewer than 179. Okay? Now, as we look at this, we see that that's too many calculations for us to use the binomial method formula. So what we're going to do is we're going to use the normal to approximate, but you need to think your way slowly through it. Now, in this particular question, it did not ask us to justify. They will have a separate question for some of the approximations. They'll have a separate part II or III that ask you to justify the use of the approximation. And if they do, that's when you do this. NP greater than 5, NQ greater than 5. Since they didn't ask that, we're just going to skip that. And we're going to go into translating our binomial information into the normal. So this is now going to be x distributed normally, and we have to do for the mean in P. So we need to do 250 times 0.65, and we get 162.5 for the mean. And then for the variance is NPQ. So just take that number and multiply it by 0.35, and you get 56.875. 56.875. So this is our new notation for the normal distribution. We also need to rewrite, so that was this one. We also need to rewrite our probability statement. Find the probability that x is less than or equal to 178. Since this was discrete, we have to go down to the next discrete value. So it's less than or equal to 178. So this is our starting point here, is converting that information from binomial to normal. Now we can go ahead and go into our Z, our standardizing, but we need to remember to do the continuity correction. Okay, so our continuity correction, since this says less than, our continuity correction is going to be the right-hand side. Okay, so remember, here's our this is our 178. So since we want to do less than, we need to start at the right-hand side so that we include the 178 block. So this is 178.5. This side would have been 177.5. And so if we were going greater than, we would have used this one. But since this is less than, we use the 178.5. So when we go into our standardization, 178.5, so that's our plus or minus continuity correction, minus the mean, 162.5, divided by the standard deviation, which is the square root of the variance, 56.875. So when we calculate this on our calculator, we get 178.5 minus 162.5 divided by the square root of 56.875, which equals 2.12. Don't forget to take 3 decimal places because it's the Z number. So 2.122, rounded off to the 3rd decimal place. Okay, so not 3 significant figures. It's 3 decimal points because we have to look up the Z number. Now that we have the Z number, we plug this into our phi Z chart. So this, we now look up our phi Z chart, 2.122. We want to look that up on our calculator here, or not our calculator, our formula sheet that they provide for us. So let's get this out of the way now that we've looked at that. Here is our normal distribution function that's in your Cambridge formula sheet they provide. And we're looking up 2.122. So the 2.1, the first decimal, is over here on the left. So here's 2.1. And then 2 is right here because it goes 0, 1, 2. So it's the 3rd column. 2.1, here's the 2. So we write down this number and we get 0.9830, 0.9830. And then we had a 2 on the end of that. So that's this, that 3rd decimal is this number over here, 2. We got to follow it all the way down to the 2.1 here. And all we're adding is a 1 onto it. So plus 1 didn't really change much. Get 0.9831. So let's come back to our board. So with the 2.1 that was on the left column of our Z chart, that's the Z number. The top number was 2. When we cross-referenced the left side with the top number, it gave us 0.9830. Then the third decimal was in the right-hand column, and when you followed it down, it said to add 1, and of course we're adding it to the end of the number. And so we get 0.9831. This number that you got from the middle of the chart is your probability, and this then is the answer to your question, the probability that you will get fewer than 179 of these 250 children that have a bicycle to 3 significant figures, 0.983. So in other words, you have about a 98% chance that you will have less than 179 of those 250 people have a bicycle. That's what it means. But this is our answer, 0.983. Okay, let's set up for another one. Okay, here's our second question that we'll pull up on the screen for you to see. It says, in Quarandon, 66% of households are satisfied with the speed of their Wi-Fi connection. Find the probability that out of 10 households chosen at random, at least 8 are satisfied with the speed of their Wi-Fi connection. Here, obviously, you see that satisfied or not satisfied is being treated as discrete. They're not giving you, an indefinite scale. It's just satisfied or not satisfied. With 66% in this first question, they have a small sample set, so it's quite easy to calculate using the binomial method. As we move on to the second part, it says a random sample of 150 households. So now the sample set is much larger. Use approximation to find the probability that more than 84 are satisfied with the speed of their Wi-Fi connection. So let's take a look at this and think our way through it. Again, your mental thought process is half the battle. The math really isn't that difficult, but you got to pay attention to those little details along the way. First, and please don't skip the notations. Very important in helping you keep track of those little details. So we're going to start with our binomial notation. Random variable that is satisfied or not, distributed binomially. N is now 150 sampled people. And the probability of success is 0.66. So that means our probability of failure is 0.34. Okay. Now we need to set up our probability statement that our random variable has more than, that's greater than, but not equal to, more than 84. Okay. So again, it didn't ask us to justify, but you can see that 150 times 0.66 would be greater than 5, and 150 times 0.34 would also be greater than 5. It does satisfy the criteria. We can use normal to approximate binomial. So the first thing that we want to do is convert our notation from binomial to normal. So our notation is now for normal, and to get the mean, we do NP. So 150 times 0.66 is 99. And then NPQ, just multiply that again times 0.34, get 33.66. That is our variance. And we also need to rewrite our probability statement because this is in discrete and our inequality does not have the equal sign. So this is the probability that our random variable is greater than or equal to 85. So 85 is the next number up from 84. Now we have the equal to, so we've taken care of our inequality issue. Now we're able to move forward into our standardization, but we need to remember to do the continuity correction. So don't get confused between these two steps. This one has to do with starting at the right point. Since it's discrete and it's greater than, we're not really starting at 84, we're starting at the 85. So looking at the inequalities helps you start in the right spot. Now, if it already had the equal sign, you don't have to change the number. It's only if it doesn't have the equal sign, you need to go up to the next value or down to the next value. This one has to do with making the discrete data continuous. So this is the starting point. This one is what makes it continuous. So what I suggest is, so that you're not wrestling with it mentally, you just draw yourself a little box right in the middle. You put your number 85 and you think, okay, this would be 85.5 and this would be 84.5. Which one do I need? I need to make sure that I take the whole box, not just part of the box. I need the whole box. This time we're going greater than, that means we're going to the right. Well, if I start from here, I'm not including the box. So I need to start from back here so that I include the box in my shading. Okay, so 84.5 is the correct number here. This is what goes down. So here's my plus or minus continuity correction. 84.5, that's the x value. So z equals x minus the mean over the standard deviation, which is the square root of the variance, 33.66. And let's figure out what this is on your calculator. So you have 84.5 minus 99. Notice you're going to get a negative value divided by the square root of 33.66. And we get a z of a negative 2.499. A negative 2.499. So this is then what we take and we put into our phi z chart. But if you remember, our z in the phi z chart does not have negative values. So we're going to have to take the positive value, and then we need to remember, because we have to make the change so that we can use the chart, we need to remember to take 1 minus p at the end. So we have to do the change of the sign. So let's go to our z chart here. Let's get rid of this. Okay, notice our z chart. The z's are positive, and we want a negative 2.4. So because we have to change it to positive, we need to remember to adjust by taking 1 minus the probability at the end. So 2.499, here's 2.4, this one I believe is the 9. So 2.49 is this one right here. So I'm going to add that 0.9936. Plus, we need to go all the way up to this 9 out here. That's the third decimal. Here's our 2.4. So the 9 out here, the 9 at the top comes down to the 2. So we need to add 2 plus 2. Okay, now we can come back here to our board now that we use that. So the 2.4 cross-reference with the 9 on the top gave us 0.9936. And then the last 9 in the right-hand column said to add 2. So we get 0.9938. But since we had to look up the positive z, we now need to do 1 minus p. So 1 minus 0.9938. It's going to give us 1 minus 0.9938. It's going to give us 0.0062. And we need to remember one other thing that I didn't point out before, and that is this one right here. Our phi z chart, if you remember from part 3, our phi z chart only works for less than values. In other words, our phi z chart always shades to the left. In our last example, we were shading to the left, so it wasn't a problem. But in this one, it wants to shade to the right. But our phi z chart gives you an answer that's to the left. So we need to do 1 minus again. 1 because of our negative z, but we need to do another 1 minus p because our inequality is facing the wrong way. So if we do 1, well, let's do it in blue. If we do 1 minus 0.0062, guess what? We end up right back with this, and if we go to 3 decimal places, 0.994, this one is our answer right here, the 0.994. Now, what we had here, if you can think ahead a little bit, you can save yourself these steps. We had to do 1 minus p because of the greater than sign. It's supposed to be less than. We also had to do 1 minus p because we had to change the z, the sign of the z. So to adjust for that, we have to do 1 minus p. Okay, so we had 2 adjustments that we had to make. Hello, we still going here? So what we had is we had a 1 minus with this one, and we had a 1 minus with this one, so that canceled each other. So notice our 0.938, we did 1 minus and we did 1 minus again, and then we got this one. So let's look at one more example. Okay, let's look at our last example here. Get it on the screen for us. It says a competition is taking place between 2 choirs. You might remember this from when we looked at it a few videos ago. The notes and the classics. There's a large audience for the competition. 30% of the audience support the notes. 45% of the audience support the classics. The rest of the audience are not supporters for either of these choirs. So as we move up, we see a random sample of 240 peoples chosen from the audience. Use a suitable approximation to find the probability that fewer than 50 do not support either of the choirs. So let's go to our board and see what this looks like. So here we have the notes, 30%, classics 45%, 240 are selected. We want to find the probability that fewer than 50 do not support either one. So let's first put this into discrete binomial information. So our binomial is our random variable is distributed binomially with 240 trials. And our probability of success is do not support either one. So if 75% support at least one, then do not support would be 25% or 0.25, which means our Q, our failure, then is the 0.75 because they actually support someone. And our probability statement is our random variable is less than 50. Okay, so then we convert X. Now we want normal. We want our mean, which is NP, 240 divided by, or sorry, not divided by, times 0.25 is 60. And then take that NPQ, multiply by 0.75, get 45. That's our variance. And our probability statement is now X less than or equal to 49, because this didn't have the equal to, so we had to go down to the next number. Now when we go into our Z standardizing value here, we need to do our plus or minus continuity correction. So we want our 49. So we either want 49.5 or 48.5. Since it says less than, and we want to include our block, we need to start here because we're going less than. We want to include this 49 as we go. And so this one will be 49.5 minus the mean over the standard deviation, which is the square root of 45. And this value equals 49.5 minus 60 equals divided by, let's do that, 49.5 minus 60 equals, it's a negative number, divided by square root of 45 equals a negative 1.565, negative 1.565. Now, in this case, our inequality is facing the right direction, but we still have this negative value on the Z. So when we plug this into our phi Z chart, we have to use the positive, and we have to remember to do the 1 minus. In the last example, the 1 minus here and the 1 minus from our inequality basically canceled out, although we did it anyway. But here, this one is already okay, so we have to do a 1 minus P once. So let's look this up in our chart, 1.565. Let's go to our screen sharing. 1.5 right here, where is our 6? Here's our 6. Come down to our 1.5, so 0.9406. Plus, we need that third decimal, which is a 5, which is over here. See, here's the 5, and it says to add 6. So we add 6, that gives us 0.9412. And we need to do, now we can come back to our board here. Now we need to do the 1 minus P that you see here at the bottom because we switched the sign to positive. So 1 minus 0.9412. 1 minus 0.9412 is equal to 0.0588. 0.0588. It's already to 3 decimal places, or not 3 decimal, but 3 significant figures. Remember, zeros on the left are not significant. So 5, 8, and 8, 0.0588. So really you have almost a 6% chance that fewer than 50 of the 240 chosen people don't support either one. And so that is the answer to our question here. So that's 3 examples of how to do normal to approximate binomial. Hopefully you've got that mental flow and process down now. Hope you can be successful in these problems. And again, as always, thank you for joining me in the Zoom room. Look forward to seeing you again next time.